Hi all, welcome back to Math 521. We're looking through the Notes 17. Um, this is the second lecture on the conjugate gradient method. Last time we saw how we could find an optimal approximation in Krylov subspaces. These were obtained by multiplying the right-hand side function by the matrix A over and over again, and looking for the optimal solution in those subspaces, optimal in the A norm. Now, if you look in the typewritten Notes 17, page 9, Theorem 2 shows you that this method is guaranteed to work and give you the exact solution after a certain number of iterations. Now, in general, if you have a vector of size n, so the linear system you're solving is n by n, then this will converge to the exact solution after n iterations in general. And what we'll see today is that you get good error estimates on the size of the error you make after far fewer iterations, asymptotically fewer in general as you let n go to infinity, for elliptic problems like the kind we've been looking at so far. So I got some overview things I'll take you through, some of the warm-up, and then I'll have a little discussion face-to-face about the typewritten notes, which have some ancient computations in them, so that's sort of amusing to look back at when I did those and the primitive machines I did them on. So the results are still the same in terms of the asymptotic behavior, but the size of the problems you can handle are much bigger today than they were than when I did those computations, which I think were in the mid-90s. You've got the notes and the overview pages, which I'll go through next. Okay, we're back in action, looking at these discussion notes. We're going to get a handle on the convergence of conjugate gradient methods using some properties of Chebyshev polynomials that were hinted at when we were talking about interpolation. The first one is, the first part from which the other things will be derived is the optimality estimate on the maximum norm of Chebyshev polynomials on the interval -1 to 1. Okay, so let me give you the framework. So we know from the recurrence relationship that we derived that Chebyshev polynomials have a leading order coefficient that's 2 to the n minus 1 times x to the n. So if I want to make a monic polynomial, I would just have to divide by this 2 to the n minus 1. And then, because I know these guys have a maximum value of 1 on the reference interval, and more than that, and this is the property that we'll use later on, the local maxima are exactly plus and minus 1 alternating in sign. Okay? So these guys have a maximum value of 1, which means that this monic polynomial has maximum value 1 over 2 to the n minus 1. And it's this property that Chebyshev polynomials optimize. If I'm looking for the unique minimizer of the maximum norm of a monic polynomial of degree n on the interval -1 to 1, it's this scaled Chebyshev polynomial that does it. Okay, and the proof goes by contradiction. Assume you have another one. This is another nth order monic polynomial that has a smaller, strictly smaller maximum norm on the interval -1 to 1. So then I'm going to look at the difference between the scaled Chebyshev polynomial and this new contender. And because they're both monic, the nth order term cancels out, and the difference is an n minus 1 degree polynomial. And I know that at every point x, this new thing, which I'm going to show can't exist by contradiction, has to have values, absolute values, less than the one that the Chebyshev polynomial has. And specifically, I'm going to look at the value of f at these particular points. These are where the Chebyshev polynomial attains its maximum absolute value, alternating in sign. So here I am. I'm looking at the Chebyshev polynomial. Let's look at j is equal to 0. That corresponds to cosine of 0, which is 1. So fn at 1 is 1 over 2 to the n minus 1. And since this guy has to be smaller, then at the 0 point, this has to have a negative value, this difference. And then if you look at the other points, you see that I have to have the sign of the difference alternating in sign between these adjacent points. Okay. Now there's n plus 1 points here. And I've got n alternations in sign, which means there has to be n zeros to this function, but that contradicts this being degree n minus 1. So that's what shows that this is the optimal thing. And if you go back to our interpolation notes, this is what shows that if you use the zeros of the Chebyshev polynomials, then you have an optimal interpolant in terms of the interpolant that minimizes the maximum value of the error over the interval minus 1 to 1. Okay, so the conjugate gradient method needs a slightly different type of optimization. So here it's going to be optimality over an interval that contains the smallest and largest eigenvalues of the matrix A. Remember, A is symmetric positive definite. So these are going to be both positive. So this is supposed to be lambda 1 and lambda 2 are positive. The polynomial that we want to find the optimality on this interval for is the one that minimizes the maximum norm over this interval, but has value 1 at the origin. Okay, so all I'm going to do is to map this interval to the reference interval and use the optimality of the Chebyshev polynomials there. So the one that's going to do the job is the Chebyshev polynomials. This is the ones that have absolute value of 1 now on the interval y, which is getting mapped to this interval. But if I want to make the polynomial have value 1 when x is equal to 0, then I have to divide by this Chebyshev polynomial evaluated at that point. So when I look at what is the minimum value of this type of polynomial on that interval, then I just get 1 over this size, because the maximum value of these guys is still 1. Okay, so now I'm going to look at this quantity, and then I'm going to remember, hopefully, to invert it to get this, this gamma. And of course, you're hoping that this gamma will go to 0 as the degree of the polynomial increases, and it will. In this case, we're thinking of the interval as being fixed, and we're looking at what happens as you increase the order of polynomial that you're allowing, keeping the polynomial values 1 at the origin. So I'm just going to divide top and bottom through by lambda 2, right? And so I'll get the Chebyshev polynomial evaluated here. Remember your assignment question, okay, where you showed that for x bigger than 1, like this thing is, right, you have this expression for the Chebyshev polynomial. So we've got the Chebyshev polynomial. If I just throw away this term, it's bigger than that. So now I'm going to go through a whole sequence of approximations, but keeping the inequality going the right way. So in all of these things, I'm putting in 1 plus a over 1 minus a, but that's bigger than 1 plus 2a, right? And then when I replace this by this in this term here, right, I have this inequality. And so that's the only term I'm going to keep. And then when I invert it, I get that this is smaller than that. Okay, so we've got an idea over how big the action of an nth order polynomial can be on this interval, keeping the value of the polynomial equal to 1 at the origin. And that's going to feed directly into the conjugate gradient estimates. Well, let's remember some stuff back from last lecture. So the conjugate gradient iterate minimizes this norm over all possible vectors in the Krylov subspace. So what is this norm? Remember, it's the inner product of this with a times that, okay? Now, I don't know what u is, right? So I'm going to go back to remembering that f is a times u, so u is a inverse times f. So I'll just put that in, and then the a and the a inverse cancels, but I'll have an a inverse over here, okay? And then I'm going to recognize this as a new inner product, right? A inverse is also symmetric positive definite. So this is a new inner product. And now I can think of this not minimizing this difference, because I don't know what u is, but it's minimizing this difference to f, but in this slightly different norm, okay? Well, not slightly, in this different norm. Okay, now let's just think about this for a minute. Everything in here in is f and some multiple of a times f with the multiples up to m, okay? So that means this a times this stuff are all coefficients of a times f and a to the power j times f, j not equal to 0, but 1 to m plus 1. And if you think about that, that makes this combination a whole polynomial of stuff in a multiplying f. And of course, because I've got this term here, right, I know that the polynomial evaluated at 0 has to be equal to 1, right? When I don't multiply by a at all, I get this f and none of this stuff, and so I've got to have that. Okay, now you can see where it's going to match up with the earlier part of the notes. So let's look at the spectrum of A. That's the eigenvalues of A. So I'm going to remember A is a positive definite matrix. So it has positive eigenvalues and a complete set of orthonormal eigenvectors. And these are orthonormal in the usual inner product. In the case of constant coefficient periodic problems, remember these eigenvectors are the discrete Fourier vectors, and we can get the eigenvalues with von Neumann analysis, but this is more general than that. This will always be true. So I'm going to start with the right-hand side, and I'm not going to actually do this computationally, but theoretically I know I can write this function as a linear combination of these orthonormal eigenvectors because they're a basis. So if I take this polynomial in A times F, I'm just going to get a sum of the polynomials of the lambdas times the eigenvalue vector decomposition of F. And if I multiply by A inverse, then I just divide all the coefficients by lambda alpha. This is the nice thing about this spectral representation of A. It's easy to take powers of A in this setting. So if I'm looking at this thing, this is the square of the conjugate gradient error at iteration m. It's the thing that minimizes this over all polynomials of degree m plus 1 with value 1 at argument 0. Well, if I take the inner product of these two things, using the orthogonality of those vectors in the usual inner product, then I just get 1 over lambda alpha, this thing squared, and this stuff squared. So now I'm going to come back to the Chebyshev argument. If I can figure out a polynomial that makes this less than m for all lambdas, then this thing is less than m squared, and I've got this thing here. Now it says repeat from the previous page because I thought I'd be doing this page by page. But under this condition, then the square of the conjugate gradient error is less than this. But remember, the exact solution is just written in this decomposition with u hat alpha equal f hat alpha over lambda alpha. And so I get this sum, but that's just the A norm of the vector. And remember, certainly in the finite element setting, this is a key norm, right? This is the natural norm of the continuum problem. If A was the mass plus stiffness matrix, then this norm here is the H1 norm of the continuous solution that corresponds to these coefficients of the basis vectors of the problem. Same argument we had at the beginning of last lecture. I guess it was at the end of last lecture when we talked about the significance of the residual. So now the question is, how small can we make m? That is, I have a set of polynomials, degree m plus 1, with value 1 at 0. And I'm looking at the maximum over all of the values of that polynomial at eigenvalue arguments. And I want to minimize over that set of polynomials. The lambda alphas are fixed. I get to play with the polynomial. Now, this is not necessarily the optimal bound for a particular problem, but generically what we can do is at least get an estimate of the behavior by saying we're not going to worry about the specific structure placement of these eigenvalues. We're just going to find the minimum of the maximum value over the whole interval between the smallest and largest eigenvalues. Okay? So once I make it a problem over the whole interval, right, then I know that I can use the result from a couple of pages back from Chebyshev polynomials, which is this result. And if you look at the square root of the maximum value over the minimum eigenvalue, the maximum eigenvalue over the minimum eigenvalue, that's the L2 condition number of this matrix. Then you get this error estimate for the iterations of the conjugate gradient method. Okay, so after n iterations, this really should be m iterations. After m iterations, I have an error in this norm smaller than that. Okay, and that means this is a number less than 1. You can think of it as a convergence factor. Every time I do an iteration, I get to reduce the error by at least that much. And you know from our von Neumann analysis that for typical elliptic problems, this condition number is size 1 over h squared. So I'm going to get a convergence factor that's 1 minus O of h. So you have to do order 1 over h iterations to get a specific error tolerance. That's the error estimate that we get from here. Now there's some further discussion in the typewritten notes, but let me just say already you know that this result may not be optimal for all matrices A. And the easy way to think about that is, let's suppose that there's only 2 eigenvalues. We can have, a minimum and a maximum eigenvalue for a large problem in which the eigenspaces associated with lambda min and lambda max have high dimension, right? So I'm going to have, dimension 100 for one eigenvalue, dimension 100 for this other eigenvalue. So I have a size 200 problem, but I will converge in 2 iterations because I just have to pick a polynomial that is 0 at the 2 endpoints. Okay, so now you can get in the game of what if your eigenvalues are clustered? So not exactly repeated, but close together in sort of groups. And then this result that we have here won't be optimal. This is essentially the optimal result when the eigenvalues are kind of uniformly spread in the interval lambda min to lambda max. And then this is the result that really applies. And in other cases, this will be an underestimate of how well the conjugate gradient method will do. Okay, I will stop there. Okay, let me just add a few notes on the Notes 17, the typewritten notes. First of all, these are quite old, and it has some discussion not just of the conjugate gradient method, but some other things that we've talked about. I don't have I've lost the text file to these notes, and so I can't update them. But there's some interesting stuff in here that is time consuming to reproduce, and so I've just left them the way they are. Now, if you go through, it's basically page 9 where today's lecture picks up. And it goes through some of the discussion that I made with my handwritten notes in the earlier part of this video. And there's a correction to equation 13, which we got in the error estimate that I showed you. The thing in 13 might be true if you raise the right-hand side to a power of k. I've been I derived something a little certainly as this factor a goes to 0, that's in the limit of large condition number. We have exactly the same thing. This could be a little bit better, a little more accurate for smaller condition numbers. which makes A larger. So you can look through and see here the reminder of the von Neumann analysis that gives the condition number. You can see the performance on some model problems. And so the thing that's funny here is, the size of problem that you could solve with the direct solver was much smaller back then than it is now. And we had some discussion of that in the last lecture we had face-to-face, I think, where I showed you some MATLAB demos where you could actually solve pretty large 2D problems with a direct sparse solver in MATLAB A/B, and there was no real delay. But remember the discussion I had before, not only were these computations much harder in the past in terms of the computational time that was required, but there was also significantly less main memory of computers, and the fill-in could max out main memory on the machines of that time. And so that was another big concern. One of the reasons why the conjugate gradient method and the pointwise iterative methods and multigrid methods were valued, not just because they increased computational efficiency, but they reduced the amount of memory that was needed. Asymptotically less main memory is needed to run those algorithms. So there's some interesting stuff in here with pictures of the spectrum, so you can see, how you can actually implement the conjugate gradient method on some spectral methods where the matrix is not sparse, but you can multiply by the matrix with a fast Fourier transform, and you can precondition a non-constant coefficient problem with a constant coefficient problem, which you can have a fast inverse for, and you can see the clustering of eigenvalues that you get in that case that leads to low numbers of conjugate gradient methods. And so that's the interesting thing. Now let me say just one final thing about sort of modern approaches. If you think about multigrid methods, I don't know if this is clear to you, but it's pretty finicky to get a multigrid method to actually converge. If the problem has strong nonlinearities and maybe convection terms, which are not positive definite terms, they're skew symmetric terms. All kinds of funny things can happen with multigrid, so that it doesn't actually converge. But a multigrid iteration can still improve the conditioning of the system. And so one of the sort of modern ideas that I think is kind of fun is they use conjugate gradient method, or if the matrix is not symmetric positive definite, there are less efficient but still good Krylov subspace solvers that fit in the same kind of framework. And you use a multigrid iteration as a preconditioner to the solve, and it can do a lot of clustering of eigenvalues that improves the performance of the system. So that's an interesting idea that combines the two numerical linear algebra things we've looked at in the course this term. Okay, so that ends the discussion of conjugate gradient method. Next lecture, I'm just going to talk about what you do with nonlinear problems. Essentially, you linearize them and use Newton iterations to solve them. And at every step of the Newton solve, you have a linear algebra problem that you have to solve. And then you use a direct solve or one of these iterative solvers on the Newton steps. And so it's iterations within iterations. And so we'll talk a little bit about that, and I'll show you an example from my own research that has spectral discretization of a nonlinear problem, implicit time stepping, which leads to a nonlinear problem for the value at the next time step. And then you do a Newton iteration on that. And at every Newton iteration, you do a conjugate gradient iteration to solve the linear system. So it's kind of fun, wraps together a few things that we know. If you haven't done it yet, on the Canvas page, I started a discussion of what people would like for a final topic. So this would be next week, a couple of lectures, one of three things that were incompressible fluid flow. It's just the elliptic part. So Stokes flow, how you handle that in the finite element setting. The other topic I have for you could be adaptive methods. So if you are computing solutions to these elliptic problems, how do you estimate what the error is, the local error, and when you should refine the grid locally? And then the third choice is discontinuous Galerkin methods. So have a look at that discussion, pick an option, register your vote by adding a comment to that discussion with your preference. Okay, and then we'll pick that up next week, and next week will probably be the last week of lectures. I think you know everything you need to know to get through the assignments, and then I'll turn you loose on your projects to be finished with the last assignment. Hopefully, April 16th is a deadline I'm hoping you can make, because then I can mark and get the marks in a timely manner. Of course, this term is full of acceptable reasons for extensions. So just let me know if that timing isn't going to work for you. I hope if you were traveling home, you got home safely, and that if you are not traveling home but staying in Vancouver, or maybe Vancouver is your home, that you're doing well here. Best of luck.